Okay, so yesterday we left off on this question, okay? So we're going to go ahead and continue on this question. Okay, so we want to calculate the amount of energy in kilojoules needed to heat 346 grams of liquid water from 0 degrees Celsius to 182 degrees Celsius. Assume that the specific heat of water is 4.184 joules per gram times degrees Celsius, and that the specific heat of steam is 1.99 joules per gram times degrees Celsius. Okay? And we have 6.01 kilojoules per mole equals the delta H of fusion. Which we don't need. Okay, so I guess we don't need that one because it's liquid already. It's not ice. It's 0 degree Celsius liquid water, so we're starting, we're just going to start from there. We're not starting at this plateau. Okay, we don't need that plateau. We're just starting right here at 0, but we don't need the delta H of fusion because, it's a liquid already. And so it'll increase its temperature as a liquid from 0 degrees Celsius to 182 degrees Celsius. So you will go to 100 and then to 182. So you will need the delta H of vaporization, which is 44.01 kilojoules per mole, equals delta H vap. Okay, delta H of vaporization. So you're going to do Q1, Q2, and Q3. And Q equals M cat. Here is your C for liquid water, and here's your C for steam. Let me know when you get an answer, the final answer. Anybody calculate an answer yet? You got one? What do you got? 1,400. Or 1047. Okay, thank you. 1047 kilojoules?
Yeah.
Okay. All right, so is anybody else getting that same answer? You got that? Okay, good. Nope, no.
What did you say all the different things were?
Okay, so Q1 will be MCAT. You'll use MCAT. So you're going to take your 346 grams of water. That's going to be your mass. Okay, your C there is going to be 4.184. And then your change in temperature is, this is 0 degrees Celsius, and this is 100 degrees Celsius. So it's 100 degrees Celsius change. Okay,
So
and that's
100 or
not each one, because the next one, there is no temperature change. Okay, Q2, we're going to use the delta H of vaporization, because it's just a simple conversion. You start with your 346 grams, convert it to moles, whatever, and then take your moles and convert it to energy using the delta H of vaporization to kilojoules. And don't forget, guys, you gotta put everything in the right units. If it's in joules, you're gonna calculate joules here. Q equals MCAT, you're gonna calculate joules, right? But it needs to be in kilojoules when you add them all together.
wouldn't the change in temperature be? I mean, is it 100 in every case, or just?
No, it's not, because
How do I figure that out?
well, because here they're saying you're starting at 0, right? And you're going to go to 182 degrees Celsius. So that means you're going to go from 0 up to 100 before it plateaus, because that's the boiling point of water, right? Water boils at 100. It will plateau there. That's when you use the delta H of vaporization. So then I'm going to start at 100 again for my Q3 and go to 182. Okay? And that's where that change in temperature will come from. So the next one's 82 degrees Celsius change. Yes, ma'am.
So for Q1, I did the grams times the temperature change, 100 degrees, right? Just part 100 times the constant.
Okay, good.
And then the grams again times the heat of vaporization.
Okay, not the grams times the heat. Because look at the units of heat of vaporization.
Yeah, kilojoules per moles.
Right, so it's not kilojoules per gram. It'd work if it's kilojoules per gram, but it's kilojoules per mole. So what do you have to do to this grams first? Exactly. Okay. Morning. We're just working on this first one. And this should be the answer. So far, that's what we've decided.
If it says 0 degrees ice, you would do delta H fusion.
If it was,
then
yes, because it has to melt into liquid water. That's what that whole fusion part is.
Right.
How much energy does it take to convert all of the ice into liquid water? And that's your delta H of fusion. Because it will not change temperature until all of the ice is melted, and then it'll change temperature. You guys getting that? Good. It's close enough. It's just rounding. Okay, if you did do the first one, then go ahead and try this one. Calculate the heat released. But this is what I want you to understand about the heat released. Which way are you going? This one we're going up. Released heat, we're going down. Okay? So your signs are going to change. because this is we're absorbing energy here. Here we're releasing energy. Okay? So calculate the heat released when 68 grams of steam at 124 degrees Celsius converted to water at 45 degrees Celsius. Okay? That's right. 124 to 100, and then 100 to 45. Because you're going to have one plateau in there. It'll be 3 Qs as well.
Is this part okay if that's joules per gram and that's the grams, or does that
Joule. This one I use with MCAT. Yeah, no, that's fine.
and then
Yes,
you just
that's
add
exactly
them
right. Convert it to kilojoules, and then add them together. Because in joules, you can't
Yeah.
add them together. How you doing?
Good, I'm a little out of it. I missed yesterday.
Okay. Yesterday's lecture is actually online. I don't know if you're
I think
You're able
I
to
found
see
it
it.
on Collaborate.
Okay,
I was
you did.
watching it yesterday.
Okay, good.
But I was also confused about which chapter we were on.
We're on chapter 10.
Okay, because on the lecture it said chapter 11.
11, yeah, that's
And
confusing.
then I was
So
looking at the notes, I was like, oh.
it is chapter 10.
Okay.
Yeah.
And
So right here we're doing heating curves, and essentially heating curves work by these areas that are plateaus are essentially the melting and boiling points. So the melting point of water is 0 degrees Celsius. I'm sorry, the freezing point of water is 0 degrees Celsius. And the boiling point of water is 100 degrees Celsius. So that gives us 2 reference points in our heating curve when we're going from 0 degrees Celsius to 182 degrees Celsius. Okay? But because it's liquid water, we're going to start at 0 without this plateau right here, because that plateau would indicate it was ice. There was ice, and it melted. Okay? Because a substance doesn't change temperature unless it's completely converted into its next phase. So it won't, once it's melting, it stays at 0 degrees Celsius until it's completely melted, and then it'll increase temperature. So that's what the plateau is about. So each one's a different Q, and we calculate the Q using that equation. Q equals MCAT, the mass times the specific heat times the change in temperature. Okay? And that might be familiar from last semester.
yeah, it's really
Okay? And so that's what you're going to use for Q1, okay, and Q3. The specific heat for water at Q1 is 4.184 because it's liquid water. At Q3, it's 1.99 because it's for steam, which is above 100 degrees Celsius. Okay, but Q2, we're going to use the delta H of vaporization. So it becomes just a simple conversion at that point. Because it's a plateau, we're not changing temperature, we can't use MCAT. Okay, so we're going to use that delta H.
So when you go back from like steam to water, is that going to be negative?
It's going to be negatives. And even the
like.
the delta H will be negative.
Okay.
Okay?
That's what I thought.
So you would switch the sign of the delta H,
Okay.
and you would make it a negative because you're releasing energy in that case. Delta H changes to a negative because it's an exothermic releasing energy now instead of endothermic absorbing energy.
So when you're going backwards, you're going to use the delta H of that, but it's going to be negative, right?
It's going to be negative. That's right.
Between the phases. So Q3 is typically what we're doing first, the 124 to the 100. And then Q1 is the 100 to the 45. And Q2
So
is-
you're doing the second question, right?
Yeah.
Okay, so yeah, so
And then Q2 would be the heat of vaporization, but to go from steam to ice. How do you actually, so the first Q3 and Q1 are kilojoules, Q2, are you multiplying that by the moles of the item to get it
Yep.
in kilojoules also?
So you have to convert 346 grams to moles,
Okay.
and then you can use the delta H of
So you use the
vaporization.
grams in the one equation, but you use moles in
In the other one.
So you have to, okay.
Yeah,
I'm
that's
saying
right.
it's like you have to do both. You have to do
Yeah,
both. Okay.
yeah.
I'm curious.
Should I do this right? I don't think I did the signs properly.
Well, if you did the signs all positive, then just switch them all negative, and it's exactly the same.
Okay.
Because it's just like adding a bunch of negatives will be exactly the same as adding a bunch of positives, just opposite. So it's going to be the exact same amount of energy, just in the other direction.
Is that right though? It seems so.
It appears. Yeah, no, it appears like you're doing it right. Yeah. What'd you get for? Did you do that second one? Who did the second one? What'd you guys get? 185. 185.2 kilojoules. Negative 185.2, right? Yeah. Okay, so this is what they're getting for the second one. Negative 185.2.
So you
Okay.
also use the heat of vaporization
You do use the heat of vaporization.
because it's at 100.
That's right, because you got to go through that plateau
Okay.
of condensation this time. It's condensing into liquid.
So fusion is only at 0.
That's right.
Okay.
So we wouldn't use it.
I'm multiplying the grams by the change in temperature times the specific heat, and I'm getting that, and I'm adding it. I guess that's 50. And then the second one is 3.777 moles times.
Okay, so Q2 needs to be your delta H of vaporization, because that plateau doesn't deal with temperature change. The temperature is held constant at 100. So that's why I use a delta H of vaporization at Q2
That's for the first one or the second one?
for both of them.
No, that's what I'm saying. I use, but it's 1.99, right?
No, the delta H of vaporization is 44.01 kilojoules per mole. This is the specific heat of steam. I use that for Q1 going down, and I use it for Q3 going up. Okay. Okay. You guys can review that. I'm going to post. This one's not going to be posted on Blackboard. I'm going to post this one directly into Canvas, this recording, okay? So I'm recording it right now, and I'll upload that recording. And that way it'll be available sooner and with less hassle of having to download the Blackboard Collaborate software and et cetera, okay? All right, so we're going to look at heating curves. Well, no, not heating curves. I'm sorry. We're going to go ahead and look at these phase transition curves, okay, and how you can use them to understand basically how a substance will be affected by the pressure and the temperature changes that it encounters. Okay? So both temperature and pressure come into play when you're going through your physical changes of solid to liquid to vapor. Okay? So this right here is a good example of a water transition. Okay? So at 1 atmosphere, which is essentially what we're at, close to, not exactly, a little below that, but we're about at 1 atmosphere. And so the water will transition between solid, liquid, and vapor at increasing temperatures. Okay? But if I decrease the pressure enough, okay, then I could actually go through just a solid and vapor transition. So that's what we're seeing here. Here is what we call the triple point, where you're at equilibrium between solid, liquid, and vapor, solid, liquid, and vapor, solid, liquid, and vapor. And you guys should look up some YouTube videos about that. It's awesome, okay? Where they'll just show that equilibrium. They'll put it into a chamber that's pressurized at a certain pressure, and then they'll increase the temperature right there to that triple point, okay, at this temperature and this pressure, and it'll just go through those changes. That substance will just go through those phase changes. It's pretty awesome, okay? But that's essentially how I would read these, okay? It's just telling me at what pressures and temperatures I can change the phases. And for carbon dioxide, okay, this one's not carbon. Oh, this one's for water again, okay? So we're looking at water for this phase diagram of water, okay? Once again, so here's the triple point for water, 0.006 atmospheres and 0.01 degrees Celsius. That would be my triple point for water, okay? Here we can see at 1 atmosphere, 0 degrees Celsius temperature, I'm going to go through that equilibrium phase between solid and liquid. Or at 100 degrees Celsius in 1 atmosphere, I have the equilibrium phase between liquid and vapor. Okay? Okay, carbon dioxide, what we're looking at, has a much higher, much higher triple point. Okay? And in fact, this is where if we buy carbon dioxide, solid carbon dioxide, okay, and it's at 1 atmosphere, then this is where we're mostly working with it, right here. Okay, carbon dioxide has a very, very low boiling point, or sublimation point, we should say, because it just goes straight from solid to gas. What would I have to do to make that carbon dioxide transition into a liquid phase? What's that? I would have to raise the pressure up to higher than 5.2 atmospheres. That's pretty dang high. Nobody wants to be in a room at 5 atmospheres, okay? But that's how I would do it. I'd have to raise it above 5 atmospheres, and then I could go through those 3 phases. Okay, I could go through solid, liquid, and vapor. But anywhere below this right here, this 5.2 atmospheres, is still just going to transition from solid to vapor. So that's why when I stick carbon dioxide on my table here, it never melts. It just simply vaporizes. The pressures are not high enough to cause those particles to melt. Okay? Okay, and you can see it vaporizes at very low temperatures, very cold temperatures. Oh, nice. And there's an example of our paper. Okay, so that's the end of the first chapter. We're going to go ahead and let's see here. Get into our next chapter. Okay, so in chapter 11, we're going to talk about solutions. Okay. So one of the main things we want to understand about solutions is that it is a homogeneous mixture. Homogeneous meaning that it is, or homogeneous, meaning that it is the same throughout. Okay? It is the same throughout the entire thing. If I take a sample of it at the bottom and a sample of it at the top, it'll be the same. If I take salt, dissolve it in water, the salt will dissolve through the water all on its own. I don't have to do anything. Those particles will separate, and they will do it perfectly. So one way you can kind of think of it is, if I'm ever trying to mix something myself, I'm never going to do a perfect job. Okay? I can sit there and mix my lettuce and tomatoes as much as I want, and it will never be homogenous. Okay? It's just not going to happen. But if the particles mix themselves, it's a solution. It's going to be homogenous. Okay? And it'll be a clear solution because the particles dissolve completely. So the solute in a solution is the item that is in the smaller or lesser amount, whereas the solvent is the thing that will be in the larger amount, the greater amount. Okay? So here we see some examples of some solutions. A gas solution is air. What is the solvent? And what is the, let's just say the solvent. What is the solvent of air? The thing in the greatest amount. Nitrogen. Our atmosphere is mostly nitrogen. And what are some solutes in the air? Oxygen, carbon dioxide, trace amounts of hydrogen, things like that, right? So we can find those things in the air. So we're breathing in all of that stuff, but only the oxygen actually gets into our lungs. Okay? A gas and a liquid. So you can see solutions don't only have to be something dissolved into a liquid, right? A gas dissolves into a liquid. Soda. Carbon dioxide dissolved into your water, and it creates soda, right? Soda water. I see this all the time where people buy a soda, it goes flat. It's flat and it's so disgusting now that they won't even drink it, right? They were fine drinking a sugary, watery substance before it went flat, and it was all tickly and carbon dioxide's tickling my throat. But after that, it's disgusting. But it's basically the same thing. So, but that's a solution. That soda, the carbon dioxide in the water, creates a solution. Okay, so other ones like H2 and palladium, ethanol and water, sodium and chloride in water, those are solutions. Here's a solid brass, copper and zinc mixture. Okay, so saturated solutions, you could imagine saturated solutions would mean that it's a solution that has reached its endpoint of how much solute is going to dissolve into that solvent. Okay? So it's the maximum amount of solute. It can't hold any more. And that's pretty true. Okay? We'll clear up a misconception about that in a second, but an unsaturated solution then would contain less than the maximum amount. And a supersaturated solution would contain more than it can hold. Wait, how does that work? Well, to supersaturate something, you have to basically put more stuff in there than it will dissolve initially. Heat it up so it'll all dissolve, because as you increase the temperature, it increases the solubility for most things, not everything. It's kind of cool when something becomes less soluble as you heat it up. That's strange, but yes, it happens. Okay, but there are, in a lot of cases, you'll heat it up and it'll dissolve into greater quantities. Okay? And then you cool it down very slowly. And as you cool it, all that extra stuff remains in there. And we say that's a supersaturated solution. So a really easy way to do this at home You take some baking soda and some vinegar. You react the baking soda and the vinegar, and this is what you're left with. So you take sodium bicarbonate, plus your acetic acid. Okay, and that's going to produce sodium acetate plus carbon dioxide plus water. Okay, so these are your products, but the carbon dioxide is a gas and it just bubbles out. Okay, the water, well, it's already a water solution, so it's just getting mixed in with the rest of the water. So all you're left with really is just sodium acetate. And if you boil away all the water, then leave just a little bit of water, it'll create a super saturated solution of sodium acetate. Okay? Sodium acetate crystals will rapidly form when you seed it. So if you have a little, or you knock it or something, but if you have a seed crystal, a sodium acetate seed crystal, and you drop it into that super saturated solution, all of a sudden everything, boom, just precipitates right out of it. They call it hot ice because it releases energy as it does that. And so here you can see the seed crystal, and then boom, it just starts coming out of solution. And because it's a super saturated solution. All that extra stuff shouldn't be in there. And so you can seed it out, right, in a way. Okay? Okay. So when we talk about solutions, okay, the different types of interactions that you'll encounter in a solution are you're going to have solvent-solvent interactions, solute-solute interactions, if you have two different solutes, and solvent-solute interactions. And this is the one that we mostly focus on, okay? And this is kind of the view of that, okay? So you have the solvent interactions between one another, the solute particles interacting with one another, the intermolecular forces between these particles, the intermolecular forces between these particles, and then you'll have a third step with the solvent-solute interaction occurring. Okay. All right, and so then therefore the delta H of a solution would be equal to this. You're not going to calculate those, but that's how we would determine that. Okay. All right, so the like dissolves like concept helps us to kind of understand what sorts of things can I mix together. So if I have a polar substance, then it is going to mix with things that are polar. That's the like dissolves like idea. A polar substance mixes with a polar substance. A nonpolar substance does not mix with a polar substance. I'm sure you guys have seen this all the time. You put your vegetable oil in water, and they don't mix. There is nothing you're going to do to make them mix. Well, that's not true. Without adding something else, there's nothing you're going to do to make them mix. Okay? They're just going to remain separate because they don't like each other. Water is polar, and it doesn't like nonpolar substances. Okay? There's just no attraction there. There's no attraction. So the slippery, greasy things just slip right out of it. Water can't hold on to it. There's nothing for it to hold on to. Okay? So that's the whole idea between like dissolves like. Nonpolar molecules are soluble in nonpolar substances. Carbon tetrachloride in hexane. Okay? They would be soluble. Polar molecules are soluble in polar solvents. So things that are polar are going to dissolve into water, which is polar. water is the main solvent for most solutions. Most solutions are comprised of ionic things dissolved into water, okay? And so that would be a lot of ionic things will dissolve in water because it's polar, and ionic molecules have polarity to them, positive and negative charges, okay? So they will dissolve. Ionic compounds are soluble in polar solvents. Now, not every ionic compound is completely soluble in water, but most of them are. Okay? So sodium chloride in water or ammonia, those are both polar substances, so they would dissolve ionic compounds. Okay, so we make solutions, and we want to make them to certain concentrations, because if we're going to carry out a chemical reaction in a solution, we want to know how much stuff we're using, right? So I make a solution, and I put so much of a solute in there, dissolve it in, and I can then take a portion of that solution and use it in a reaction. Okay? But I want to know how much stuff I'm using when I take a portion of it. So we want to base that on concentration. And the units of concentration for solutions, one are percent by mass is one of those. Percent by mass is equal to the mass of the solute divided by the mass of the solute plus the mass of the solvent times 100. Okay, so looking at that, if I was to say you had 16.5 grams of sodium chloride in 275 grams of water, how am I going to determine the mass per mass percent? Okay, so what goes on top? Okay, 16.5 grams of sodium chloride goes on top over 16.5 grams of sodium chloride plus 275 grams of H2O, right? So that's how I do the mass per mass percent times 100 to get a percent. Okay, now I have the mass per mass percent. All right? So it has to be over the total. And that's pretty much what a percent always is. The part divided by the whole times 100. That's always what a percentage is. The part divided by the whole times 100. Okay? Okay. So that's one concentration unit. So here's another way to look at that, right? Mass of the solute over the mass of the entire solution times 100. And we'll find our percent. Mole fraction. Mole fraction is also kind of like a percentage, but then just not multiplied by 100. Okay? But it's the same idea, but instead of doing it by grams, which is what we're doing here for mass, we're going to do it in moles. And we're going to use what we call the mole fraction, which if you think of it as a percentage can help you understand it because it's just not divided or multiplied by 100. The moles of component A divided by the moles of everything. Okay? The part over the whole. And it's a fraction. So it's a decimal. We don't say it's a percent because we don't multiply it by 100, but it's the same idea. if I multiply something by a mole fraction, then it's essentially multiplying it by its percent. Okay? The percent of moles of A in that substance. Or if I wanted to find the mole fraction of B, I would say moles of B over the sum of everything. Or the mole fraction of C, the moles of C over the sum of everything. Okay? Okay. Let's go to this next one, and we'll go back to that. Okay, another concentration unit, molarity. Molarity is probably the most common one that we use. You guys did molarity last semester, right? So molarity is the moles of the solute over the liters of solution. And when I say liters of solution, you mean the final amount, okay? So that solution measures to 1 liter. So you first you want to dissolve your thing into, and then dilute to exactly 1 liter. That's how you're going to create a 1 molar solution. You can't get a liter of water and then put your stuff in, because that will raise the volume above it, above the liter, and then it's not a 1 molar solution or whatever you're trying to accomplish. Okay, so you have to dilute it to exactly 1 liter. So when we say liters of solution, we know exactly what that volume is. The final volume is 1 liter of solution for molarity. Okay, for molality, did you guys talk about molality? Molality is essentially kind of the same as molarity, except instead of using moles per liter, we're using moles per mass. Mass of the solvent. How much does the solvent weigh? Okay, that's what we're doing here. So if the earlier question with the sodium chloride, in this case, I would first find the grams of the sodium chloride. I'm sorry, the moles. I'd find the moles of the sodium chloride, and then I would divide it by the mass of the water on the bottom. Okay, and that would be my molality. So if you are given one of them, so this is what you kind of need to be able to do. If you're given one type of solution, you need to be able to convert to the other type. Okay? So if you're given molality, you need to be able to convert to the molarity. Or if you're given molarity, you need to be able to convert to the mole fraction. Or if you're given the mole fraction, you need to be able to convert to the mass per mass percent. Okay? So this is what you're going to have to be able to accomplish in this section. Okay? So let's try a few examples then. Yes. Okay? What if you have a 3.65% magnesium chloride solution? It's in water. Solution in water. Okay? What is what is the mole fraction of magnesium chloride? Okay, so for this question, to approach it, first I want to get rid of that percent. Okay, I want to convert it into its decimal form. So it's 0.0365 grams, basically, of magnesium chloride for every 1 gram of solution. Okay. So this is kind of where I am. This is my starting point. And I want to get to the mole fraction. So what is one of the first things I want to do? Convert to moles. Okay? So I want to take that 0.0365 grams and I want to convert it to moles. 0.0365 grams of magnesium chloride. And I'm going to convert that to the moles of magnesium chloride from the grams of magnesium chloride. So it's a simple one-step conversion here from grams to moles. Okay? Whenever I have grams and moles together, moles are always 1. So that's what's going to go on top. And then what number am I going to put down here for the grams of magnesium chloride? The molar mass. I have to find the molar mass. Okay? So what is that? That's 71 for chlorines, and then magnesium weighs 24. 95.2. Okay. Okay, 95. Okay, 95.2 grams of magnesium chloride. So 0.0365 divided by 95.2. What do we get? Say it louder. I'm sorry, guys.
3.8.
Okay. So that's how many moles of magnesium chloride I have. That's step 1. Okay. So to get the mole fraction of magnesium chloride, that would be my top number, right? Now what? Okay.
So we need the grams of water.
I need to find out what the grams of the water are. How am I going to do that? 1 minus 0.0365. What is it? Okay, so 0.9635 grams of H2O to the moles of H2O from the grams of H2O. 1/18. Okay, so 0.9635 divided by 18, what do you get for the moles of water? 0.5. Whoa, that's weird. 0.054 moles. Okay? All right. Good. Now I have everything I need. So the final equation will simply be 3.83 times 10 to the negative 4 moles divided by 3.83 times 10 to the negative 4. Where did my negative 4 go? Moles plus 0.054 moles. And I will find my mole fraction. Good. Okay? So yes, that's how I would do that. To go from the percent of magnesium chloride, 3.65% of magnesium chloride, to the mole fraction. Okay? All right, let's try, let's see, I have another blank page. Okay, let's try another one. Oh yeah, absolutely. Okay, I'm going to move forward. We're going to try another one. Okay? You have a 1.85 molar solution of potassium sulfide. No. Okay, 1.85 molar solution of K2S with a density of 1.15 grams per milliliter. What is this in molality? How am I going to get to the molality? Okay, well first let's break down what this 1.85 molar solution is. Okay, 1.85 moles per every 1 liter of solution. Solution. Okay, liter of solution. It's 1.85 moles of K2S in 1 liter of solution. I don't need to change this, right, because I'm going to use that in my next equation. What is the equation for molality? Anybody remember? Moles over kilograms of solvent, not solution. Solvent. Okay? That's a big difference. It's a big difference because, yeah, that would be so easy to take the 1 liter, use the density, convert it to grams, boom, boom. Okay? It's not that easy, guys. There's another step there. So what do I have to do? Yeah. How am I going to do that? I do. I need to figure out the solvent. What information did they give me? Now, I'm not saying you shouldn't convert it from liters of solution to grams. Good. That's what I want to do. Okay? So I want to convert this to grams from the, so this is 1,000 milliliters, okay? From the milliliters, so 1.15 for every 1 milliliter, okay? So 1,000 milliliters times 1.15 grams. How many grams of solution do I have?
11,000.
Okay, so I have 1,150 grams of solution. Now what do I do to find the solvent? I do need to subtract the solute like you're saying, but how? It's in moles. I got to convert it to grams. Good. Grams from the moles of K2S. So 1 mole for every how many grams? So what is that? 78 plus 32. What is it? 110? Okay. So 1.85 times 110, how many grams is that? Say it louder. 235? Thank you. Grams of solute. There we go. Now we have what we need. Okay? So I can subtract this from the 1,150, and that will tell me the grams of solvent. Okay? Once I know that, I can take my 1.85 moles of K2S, 1.85 moles of K2S, and I can divide it by the mass of the solvent, which is what? Oh, I missed a step. What did I miss? Kilograms. So it's 0.9465. There we go. Now we've got it. 1.85 moles of K2S divided by 0.9465 kilograms. I see some concerned looks out there. Okay, so it's just the mass of K2S because we're going from the moles of K2S to the grams of K2S. The periodic table. Okay. Yeah. And then get the 946. Okay. So this is the grams of the solute. This is the grams of the solution. The solution is made up of both the solvent and the solute added together. So if I subtract the solute from the solution, I'm left with 946.5 grams. And that's how much the solvent weighs. Because we know how much the solute weighs, we don't know how much the solvent weighs. Okay? Okay, so here's another example. What is the molality of a 5.86 molar ethanol solution whose density is 9.27 grams per milliliter? Okay, you guys do this one. What is the molality? This is just kind of like what we just did. What is the molality of a 5.86 molar ethanol solution whose density is 0.927 grams per milliliter? the units would then be, oh, I see. No, you calculate it and it'll be molality would be the new units. Moles per kilogram would be the molality. You just call it, just like with molarity, you assume it's moles per liter. Molality is moles per kilogram. Yep.
So what would the units be for
For mole fraction, do we do mole fraction doesn't have any units. Yeah, it would be units. It's essentially like a percentage. Yeah. Okay, is this what you guys were getting to? Okay. 5.86 moles of ethanol is 270 grams of ethanol. And you had 927 grams of solution. If you use the density to determine the amount, 927 minus 270 is 657 grams of ethanol. And then you take that into kilograms, and you'll have 5.86 moles, which is what you started with, divided by the 6.657 kilograms, okay, of solution. And that will find you your molality of 8.92 molal. Okay? All right, so you're going to have a number of these on your homework. So you'll get lots more practice, okay? So we're already into the second homework. So the first homework I'm going to make due the end of this week. The second homework I'm going to make due on Monday, okay? So make sure you're keeping up with those. Don't leave them till Monday, okay? Don't leave the second homework till Monday. I will get through the first one as soon as you can and get through the second one because you're just going to start to fall behind otherwise. Okay. So solubility generally increases with temperature. So you can see for potassium nitrate, that's definitely true, okay? So here at a temperature down here of 0 degrees Celsius, okay, that's not very soluble, but as you increase the temperature, okay, it becomes very soluble. And the solubility is described by grams of solute for every 100 grams of water here in this case, okay? So if I have 100 grams of water, how much solute can be dissolved into it. Okay, and you can see most of these are upward curves. But then here, look at sodium sulfate. It actually has a downward curve. Okay, because its solubility decreases with temperature. It'll precipitate out as it gets hotter and hotter. Okay, along with the cesium sulfate. We'll do the same thing. And they're not very soluble in the first place. Okay. Sodium chloride, you can see its solubility is pretty constant through the temperature scale. So it's very soluble here at 0 degrees Celsius, and it's very soluble here at 100 degrees Celsius. Okay, you can get those 50 grams. But for the idea is that if you increase the temperature, you're going to increase the solubility of that item. Okay, and then those are the decreases in solubility. Fractional crystallization. We're kind of going to do this in the lab tomorrow. You're going to crystallize and recrystallize your product to purify it. Fractional crystallization is the separation of a mixture of a substance into its pure components on basis of solubility. So, for example, the potassium nitrate. Let's see, I think they give us an example here. Suppose you have 90 grams of potassium nitrate contaminated with 10 grams of sodium chloride. Okay, so how am I going to purify the potassium nitrate away from the sodium chloride? So you dissolve a sample in 100 milliliters of water at 60 degrees Celsius. Okay. And then cool the solution to 0 degrees Celsius. All right. And as you cool that, all the sodium chloride will stay in solution. Okay? All that, because it's 10 grams of sodium chloride, right? So at 0 degrees Celsius, more than 10 grams of sodium chloride can remain dissolved into there. It's 38 grams per every 100 grams at 60, okay? And as you cool it, it doesn't change that much. So it's going to remain around there. Okay, 34.2 grams for every 100 grams of water, okay? So I can have more than 10 grams of sodium chloride dissolved, and it will remain dissolved. However, once I drop the temperature to 0 degrees Celsius here, only 12.1 grams of the potassium nitrate will remain dissolved. So I had 90. How much of it's going to precipitate? Yeah, exactly. Okay, and just subtract that 12.1 grams from it, and 78 grams of pure potassium nitrate will precipitate as a solid. Okay? Good. So that's what we mean by fractional crystallization. Okay. So, gases, and their solubility and temperature also. Okay. You can see that as the temperature increases, what happens to the solubility of the gas? It also decreases. Well, that makes sense. Has anybody ever left a soda in the car in the hot summer and then opened it later? Those gases are trying to escape. They're going to try to escape, right? They're trying to get out of there. So the solubility of the gases will decrease with temperature. Okay. So when we talk about these solubilities of gases, Henry's law helps us to see that the concentration of the gas is proportional to the pressure that's being exerted above. The concentration of the gas inside the solution is proportional to the pressure that's above it. So if I increase the pressure of the gas above that solution, what happens to the concentration of the gas in the solution? It also increases. Okay? So this K is a constant that would help us to determine the concentration of the gas inside the solution at those pressures, at any pressure. As long as we knew K and the pressure, we could find the concentration. Or we could find the pressure if we knew K and the concentration. Right? So Henry's law is pretty basic, straightforward. It's pretty easy to use. But the idea is that these gases will create an equilibrium inside of them. Okay? So as one molecule escapes, another one will dissolve back in. And you'll create an equilibrium, a dynamic equilibrium between these gas particles. They're coming in and out, in and out, in and out at the exact same rate once they're at equilibrium. And it will maintain the concentration inside of that gas, of that solution. So your soda is the best example, right? So once I open that soda, what happens to the gas that was above it? It escapes. Okay? So then I close it back up, and what has to happen? It has to re-equilibrate. So some of those gas particles are going to come out of the solution, and they're going to fill that void. It's now void of those. It's now void of these gas particles, so it's going to fill it until they re-equilibrate, and then it will maintain that concentration in the solution. So if I have, let's see, if I have a soda bottle, this is a great soda bottle, okay, and it's full, then I'm only maintaining the concentration of this area right here, okay? Because we can pressurize it, and the soda company is going to send it with the pressure. The carbon dioxide is pressurized right there, and it's maintaining the carbon dioxide in the solution. But then I open it, and that carbon dioxide escapes, okay? So this escapes, and then I drink some. Now I have a bigger void, right? And I don't have any more gas. So these particles have to escape to fill this void. And what's going to happen to the concentration of the carbon dioxide in the soda? It's going to go down until it reaches an equilibrium. Once it's at equilibrium, it will maintain the concentration once again here. Okay? So what are some ideas of how could I keep more carbon dioxide in here? What could I do? I could do that. That would change the volume here, right? If I change the volume here, there's less void to fill. So yeah, I could scrunch it. If you have a 3-liter bottle, that's a really good idea, because you drink half of that 3-liter bottle and you stick it in the fridge, and it's just the next day you come back and throw it away. Okay, because it's just so flat. But that's because there's like this much area to fill with gases to re-equilibrate. So if you just crunch it down, and then put the top, like just smash it, get all that liquid up into there, and then put the top on, keep it in your fridge, it'll stay more carbonated. Okay? And what else? What else could I do? I could repressurize it with carbon dioxide. Okay? So I could repressurize it with carbon dioxide, and that would maintain the concentration of the carbon dioxide in the soda. Could I repressurize it with just atmospheric air? Is that going to do anything for the carbon dioxide in the solution? No. All I'm going to do is start oxygenating it and putting nitrogen into my soda, right? I don't care about those things. They don't tickle my throat. They don't burn my intestines. So I don't want that. Okay? I want the carbon dioxide. And if I don't get it, I'm going to throw that thing away. Okay? So I could repressurize it. So that's a hard thing to do unless you have a source of carbon dioxide gas, right? Or if you put a piece of dry ice in there, which I do not recommend because you'll create a bomb. That'll be a dry ice bomb if you don't put the right amount. So don't do that. But yeah, that's, you could, maybe some baking soda might repressurize it with carbon dioxide, but that might change the taste a little too. But, so, because the baking soda would react with the acid because soda is acidic, and that would cause some carbon dioxide to be created. But yeah, that's a hard thing to do. I think the easiest, safest way is to just close the volume, make the volume smaller, and then close it off, okay? We won't talk about dry ice bombs from graduate school. Okay, so that's Henry's law. Excuse me. Okay, yes. If we increase the pressure, it'll be high concentration. All right, collegiative properties. Collegiative properties are properties that are not dependent on the identity of the solute. They don't care what you are. All they care about is how much there is. So the collegiative property will change to the same extent whether you are a sugar molecule, or whether you are a sodium molecule, or whether you are a chlorine molecule. They don't care. Okay? Collegiate properties change dependent on the concentration of the total particles in the solution. Okay? All right, so vapor pressure is a collegiative property, vapor pressure lowering. And vapor pressure lowering is identified here. This X, whenever you see these kind of X's, we're talking about basically the mole fraction. Okay? So the initial pressure, sorry, not the initial pressure. That would be this one. Okay? So the vapor pressure lowering is determined by the mole fraction of the thing that's in there times the initial pressure. Okay? So this is going to tell me how much it's going to lower that vapor pressure. So once again, mole fraction is like a percentage. I'm multiplying this pressure by the percentage of the moles, basically. And that's going to tell me my new vapor pressure. Okay? Okay. That's so the vapor pressure of the pure solvent is P0, and the mole fraction, and that's if its solution contains only one solute. Okay. All right. So obviously, if we want to find the other thing in there, then x1 equals 1 minus x2, just like we did earlier to find if we were trying to convert from percentage to mole fraction. Okay, so 1 minus the mole fraction of the other thing will give me the mole fraction of this thing. Okay, so if I need to know what that is, then I can easily do that in that way. Okay, so here we get kind of a simplified version of the change in the pressure is equal to the second mole fraction of 2 times the initial vapor pressure, okay, which would essentially be the initial vapor pressure minus the new vapor pressure, okay, of P1, the vapor pressure of P1, and that's my change in vapor pressure. Okay, so that's going to lower the vapor pressure. If I dissolve something into a solution, the vapor pressure will decrease. So what do I mean by the vapor pressure? I mean the pressure that accumulates above a solution. So if I have water in a cup and I put a lid on that cup, okay, I put a lid on that cup. Here's my cup. I have a lid on it. This is the water. Water is going to evaporate inside of the cup, and it will start to condense. It'll create an equilibrium once it reaches the correct pressure above the water. okay? And that pressure will maintain the volume of the water that's there. So if I dissolve something in the water, though, so if this is, let's say the vapor pressure here is 22.5 torr, okay? That's the vapor pressure of the water, pure water. But if I dissolve something into it, okay, that's going to change the vapor pressure of the water. It's going to lower it. So it might go down to like 20.3 torr because I dissolved something into the water. And it doesn't care what you dissolved in there. It doesn't matter what it is. If you put something in the water, it will lower the vapor pressure, okay? And if we know the mole fraction of that thing, then we can find the change that occurred in the vapor pressure, delta P, right? And then if we know the initial vapor pressure, we can find the new vapor pressure from the change in the vapor pressure, okay? Okay. Okay. Mole fraction of the solute. Yes. Okay, so this is just kind of P total, the pressure of the benzene, and the toluene, the vapor pressures of those things. So this is two things. If you mix it, and they will have these different pressures. Okay, so the mole fraction of benzene here. Okay, as you increase that mole fraction, then what does it do to the vapor pressure of the toluene? This is because both of these things have a vapor pressure. Okay, that's what it's considering. Okay, both things have vapor pressure. So if I increase the concentration of the benzene, how does that affect the pressure of the toluene? Okay, and so it's definitely changing that. It's lowering that vapor pressure of the toluene as this is increasing. Okay, yes, and we're not really going to do a lot of these solvent, volatile solvent mole fractions, or vapor pressure lowerings. Okay, this is just an idea of how you can separate different solutions by their temperatures, right, through distillation. So here I have a mixture of things, and I want to isolate them at different temperatures. So one will have a boiling point lower than the other one. Okay, so as I boil the first one away, I can collect it because this is a condenser with water. It'll go through here and it'll condense up in here in the water. Not in the water, but it's surrounded by a water condenser. This is a tube that's a glass tube that's the water is cooling the tube, so as it comes here it condenses and you can collect it there. Okay, and so you can separate those by their different boiling points through fractional distillation. Okay, so another colligative property is boiling point elevations. So if I dissolve something into a solution, if I dissolve something into a solvent, it will change the boiling point. It will elevate the boiling point. It will always elevate the boiling point. Okay? No matter what it is, I will change the boiling point of that solution. Okay? All right. And you will also have, they're showing that here too. Okay? So this is the boiling point of water. If I dissolve something, it changes it to a higher boiling point. The freezing point of water, if I dissolve something, it will change the freezing point by depressing it. So boiling points elevate, freezing points depress. It's always like that. No matter what I put in the water, it will always increase the boiling point and decrease the freezing point of the water or of any solvent, okay? Because these are colligative properties. Yes. Okay, now this is the equation that we use, but I'm going to add something to this equation. Not that one. Where is it? Yes, there it is. Okay, so the change in the boiling temperature, which is initial, final minus the initial boiling temperature, okay? And that's going to equal my Kb, which is a constant for whatever solvent you're using. So if it's water, I have a boiling constant. The boiling constant for water, I believe, is 0.52. 0.52 degrees Celsius per mole. That would be the boiling constant for water. Okay? So every unit of molality will change the boiling temperature by 0.52 degrees Celsius. That's what this is telling me. Okay? So, if I know the molality of the solution, then I simply multiply it by 0.52, and it'll tell me that it will change by this many degrees Celsius. Okay? And then to find the new boiling temperature, I would simply need to take that change. And if it was, let's say your boiling temperature was 100, and it changed by 5.6 degrees Celsius, then your new boiling temperature is 105.6 degrees Celsius, because that's the change. Okay, so that's how I find the new boiling. So you need to make sure you're answering the question. If it's asking for the change, then you solve for this, and you find the change. If it's asking for the new boiling temperature, then you need to solve for the new boiling temperature by subtracting it, or I'm sorry, adding it to the initial, okay, temperature, which was 100, and then I added. But with freezing point, it depresses, so you would subtract it. Okay, so you have to be aware of that. Okay, so I'm actually going to add a little factor here, and this is how you'll see it on your reference material. I, okay? Delta TB equals KB molality times I. And we're going to define I as the von Hoff factor in a minute, okay? But that I is going to be very important. We have to consider that every time, what it is, okay? We'll get to it. Okay, and M is the molality, not the molarity. The reason we use molality is because mass of a solution will not change with temperature. It doesn't change with temperature. But volume of a solution does change with temperature. So if it's molarity and I increase the temperature, the volume could change. But if it's molality and I increase the temperature, it stays the same. Okay? So when we're working with colligative properties, we use molality because it will remain constant. Wow. Okay, guys, we need to take a break, huh? Yeah, let's take a break. 10 minutes. You guys just let me keep going and going and going. Hello.
I got completely lost on this one, but I think find the molality. The second one. Okay. Go ahead if you have a